Hey folks, Professor Gray here, ready to talk to you about sampling distributions. The normal distribution is an incredibly useful thing in statistics, in part because it shows up so very often in natural phenomenon, but also because of how it allows us to find probabilities in a sampling distribution. Now the sampling distribution, the one we're going to talk about is of the sample mean, is the distribution of all possible sample means with all samples of size n taken from the same population. So instead of looking at individual values and how they're distributed, we're talking about means, averages of all the same sample size and how they're distributed from the same population. The mean of the sample means is the population mean. So mu sub x bar, that's mean of sample means, is equal to mu. And the standard error of the mean is used as the standard deviation of the sample means. Sigma sub x bar is equal to the standard error of the mean. The formula for that is sigma divided by the square root of n, or population standard deviation divided by the square root of the sample size. Now, sampling distributions, even though they're bell-shaped, just like a normal distribution, they're taller and they're more narrow. So the curve is taller and the sides are pushed in more. And it's just like you've squeezed a normal distribution and the area has nowhere else to go, so it pushes out towards the top. As mentioned earlier, normal distributions are made up of individual values. The sampling distributions are made up of mean values. And we reflect that when we write the probability statement. So we'll use notation like this. Capital P for probability. So probability of, parentheses, x bar is less than or greater than or in between two values. Now if you're using a standard normal distribution, instead of the x bar, we'd use a z. If you're using a non-standard normal distribution, instead of the x bar, you would use an x. For sampling distributions, since we're dealing with averages and mean values, we use x bar. Now here's the central limit theorem. It says with all samples of size n, the sampling distribution of x bar can be approximated by a normal distribution with a mean of mu and a standard deviation of the standard error of the mean. If the parent population is normal, if the population all this is happening from is already a normal distribution, then n, that's the sample size, can be any size. It gets grandfathered in, so to speak, or it inherits its normality. Now, if the population that all this is happening from is not already a normal distribution, or if we just don't know if it's a normal distribution or not, then the sample size needs to be at least 30 for the mathematics to work and the central limit theorem to take hold. The central limit theorem is one of the more important theorems or ideas in an introductory statistics course. Well, how can we tell if we're dealing with sampling distribution? Well, you can look for questions about mean values from samples of size greater than 1. So it's like this. In this top question, we have what's the probability that a score is greater than 5? Okay, that's talking about one score being greater than some number. So that would be a normal distribution problem. Versus the bottom question was the probability that the mean of 35 scores is greater than 5. In the bottom question, we're being asked about the mean value of more than one score. So it's a sampling distribution problem instead. Well, to solve these types of problems, we'll use normal CDF from the calculator. Normal CDF can be found in second bars. Now, we've used this command before for other normal distributions. We have to make one adjustment for a sampling distribution. Because the distribution is skinnier and taller, we have to adjust the spread. That's the standard deviation. So you change the last number that goes into the calculator to the standard error of the mean. So we'll start with the lower limit, then the upper limit, then the mean, and lastly the standard error of the mean. And there's no need to calculate and round it before you put it in the calculator. You can type it in its entirety, and the calculator will do the calculations for you with avoidance of round-off error. Let's do some examples. Assume that women have heights that are normally distributed with a mean of 65 inches and a standard deviation of 3.5 inches. 22 asks, if 36 women are randomly selected, then what's the standard error of the mean? So for number 22, I already have the formula written down. Standard error of the mean is sigma over the square root of n. Sigma is the standard deviation of the population, so that's 3.5. Lowercase n is sample size. The problem says 36. Now we can put that in the calculator and find our answer. We'll round that answer to 2 decimal places, since all our other decimals in the problem are rounded to 1 place. So we get 0.58. That's the standard error of the mean for that particular scenario. Number 23 says, what's the probability that the mean height of 30 random women is between 63 and 67 inches? For this one, I'm being asked for a probability. It says, literally, what is the probability? And notice, I'm talking about 30 women, so more than one, and their mean height, or their average height. This is a sampling distribution problem. So first, my statement. All right, the probability of 63 is less than x bar, because it's the mean height, is less than 67. Then I make a sketch. Remember the 4 S's. Probability statement, sketch, syntax, and solution. For my sketch, I'm finding the area between. So I'll need the area like this. Do make sure that your numbers are at least on the correct side of the middle, correct side of the mean. Remember, the mean is always in the middle of the distribution. Now for the syntax. We're going to use normal CDF. Start with the lower number, in with the upper number, then the mean, 65. And lastly, since this is a sampling distribution, we need to put in the standard error of the mean. So standard deviation is 3.5 divided by the square root of the sample size. For number 23, our sample size is 30. So far, the only thing that's really different from a usual normal distribution problem is the notation changes just a little bit. And this last number in the calculator command changes. When you put that in the calculator, you can do it like this. All right, when I go to put in my last number, the standard error of the mean, I can just type it directly in. I don't have to find it and round it and then put it in first. I can just do it all at once. Now on my calculator, I'm going to need to end my line with 2 closed parentheses, one to close the stuff underneath the square root, one to close the command. Yours might differ. And that's it. I have my answer. We round probabilities to 4 places typically, so 0.9983. That's the answer. It's also the area underneath the curve between 63 and 67 in a sampling distribution. Now, the central limit theorem is important because it allows us to do what we just did. That is, using normal CDF, the area under a normal curve, to approximate this sampling distribution probability. Let's do some more examples. Same setup. Let's do number 24. Number 24 says, what's the probability that 30 random women have a mean height less than 63.4? All right, 63.4 would be to the left of the middle. Area to the left would be less than. So technically that starts at negative infinity and goes up to 63.4. Alright, so my calculator command, since I don't have an infinity sign in the calculator, I'll need to pick something so far to the left that it won't make any difference for rounding. So let's do negative 1 million. Could have done negative e to the 99th. You could have done negative 10,000. All those would work in this context. We'll stop at 63.4. Put in our mean at 65. And then the last number, remember this is more than one score and it's actually a mean score. Standard error of the mean is 3.5 divided by the square root of your sample size, which is 30. That part's different. Alright, second var's number 2 for me. Remember to use the negative button, not the subtraction button. And you get your answer. 0.0061. Number 25 says, what's the probability that 30 random women have a mean height greater than 64.1 inches? Well, let's find out. 64.1 is going to be a little bit to the left of center. Remember the mean's in the middle, and that's 65 in this case. And I'm going to need the area to the right. So normal CDF. Start at your lower number. Go up to some extreme positive value. Put in your mean, in this case 65, and then your standard error of the mean, because again the sample size is bigger than 1 and we're talking about a mean value, not an individual value. 3.5 over the square root of the sample size, which is still 30 for this problem. Second bars. And we get our answer, which is 0.9205. Here's a new setup and a few more of these types of examples for you to review. The United States quarters have weights that are normally distributed with a mean of 5.670 grams and a standard deviation of 0.062 grams. Number 26 asks, if 12 quarters are randomly selected, then what is the standard error of the mean? My answer is 0.0179. Number 27 asks, what's the probability that 20 random quarters have a mean weight greater than 5.657 grams? For this problem, I'm finding a probability, so I use normal CDF. Since this is a sampling distribution, I need to change the last number to the standard error of the mean. And my answer is 0.8258. Number 28 and 29 have the same setup. Number 28 asks, what's the probability that 20 random quarters have a weight less than 5.624? For this particular problem, the answer may look strange at first, but if you notice on the right-hand side, I have a lower or a smaller uppercase e, -4, so that's scientific notation. We'll need to do a little work on the answer. So that's 4.5 times 10 to the -4th. Take your decimal, move it 4 places to the left. That gives you, all right, I'll move it 1, 2, 3, 4. I get 0.00045. Then round that to 4 places. So I get about 0.0005, and that's my final answer. When you have scientific notation given to you from the calculator, convert it out of scientific notation first, and then round to the number of decimal places that you need to. Now let's do number 29. It says, what's the probability that the mean weight of 20 random quarters is between 5.668 grams and 5.672 grams? And my final answer is 0.1147. In summary, the normal distribution is extremely common and important. Normal distributions show up in a lot of natural phenomenon, like heights of trees, heights of people, circumferences of trees or plants. Different natural phenomenon often results in a normal distribution. That's one reason it's very important. The other reason, or another reason, is things like the central limit theorem, where we can use a normal distribution to find probabilities even if we don't know anything about the parent population that we're talking about. As long as the sample size is big enough, we can use the central limit theorem and normal distributions, and we don't really have to even know if the population is normal or some other sort of distribution.